Okay, pressure and upthrust. So again, more pressure. The first thing you need to know is, why does pressure in a fluid depend on the density of the fluid and the depth of the fluid that you're in? And we've discussed that already in 15C. Okay? So if you go deeper into the fluid, you are going to have a greater weight of fluid pushing down on you. It's that simple. Because you know the pressure is equal to the force per meter squared. So if you go deeper, then you will have much more fluid above you. You have more fluid above you, there's a greater force. The weight of the fluid pushing down on you will be greater, so the pressure on you will be greater. Okay? So the reason that pressure depends on depth is because the deeper you are, the more fluid you have, therefore the greater weight of fluid is acting down on you. Density. Again, if you have a fluid above you pushing down, okay, creating that pressure, and the density of that fluid is greater, then there is going to be a greater weight pushing down on you again. Alright, so in both cases, density and depth both increase the pressure because of the weight of fluid pushing down. If you have a greater density, there will be a greater weight pushing down on you, and if you have a greater depth, you have more fluid, and therefore you have a greater weight pushing down on you as well. Okay? So the pressure on an object in a fluid, the way that we look at it, because again it's per meter squared, we say, imagine just a column of fluid, like a meter squared column, and you go up, so on top of the object here, the same in the textbook, you have a column just from the fluid. Of course, you have the whole atmosphere as well, so you have the 100,000 pascals from the atmospheric pressure, but we're not really considering that. We just want to know, what is the pressure of this fluid, this water, pushing down on top of this fish? Okay, so we take the column, 1 meter squared column, we go up to the top of the surface from the fish, then the pressure acting on that fish at the time for the column equals the height of the column. Now the height of the column is same as the depth in the water. Okay, the deeper the fish goes, the higher the column becomes. So the pressure on the object in the fluid is equal to the height of the column of fluid above times by the density of the fluid it's in. Okay? The higher the column of fluid, i.e. the deeper you are, the greater the pressure. The greater the density of that column of fluid, the greater the pressure. Because again, the greater the density, the greater the weight, the force that you're going to experience, okay, above you. Alright? And also G. So pressure equals the height of the column of fluid, or the depth in the fluid, times by the density of the fluid, times by the gravitational field strength G. Because again, all of this is dependent on a weight pushing down, and the weight pushing down on you due to the fluid is obviously because of the gravity. Alright, so it would be different if you had a different gravitational field strength, but obviously most of these questions are going to be for on Earth. So the pressure acting on an object due to a column of liquid is the height of the column, or the depth in the fluid, times by the density of the fluid, times by G. Okay, that's just a value. Calculate the pressure on this object. If it's this distance under the surface, okay, if the density of the fluid that it's in is this, and G is obviously 10, then I can say the pressure on top of this object is this. Alright? Using this and moving on from this, we can actually look at upthrust and objects floating. Okay? Everybody knows upthrust is an upwards force. Most of the time people can often say there's upthrust acting on this container on the desk. That's not true. Upthrust is provided by fluids. So you either experience upthrust if you're in a liquid, or you can experience upthrust if you're in a fluid. So even falling through the air, you will still have an upthrust force on you because of the air, but the biggest force acting up would be air resistance and drag. So the upthrust force when you're falling through air is very small, you can neglect it. Okay? But in a fluid, obviously, it helps you float. It keeps objects up. So the upthrust on an object is force on objects in a fluid upwards, we know that. But it's due to the difference in pressure between the top and the bottom. That is the most important part of what is upthrust. Okay? Question in the exam. Define upthrust. Why is upthrust present on an object? Why does upthrust occur? Why is there an upwards force from a fluid? Okay? And it's because there is a difference in pressure. So back to the fish, or any object that is in a fluid. Okay? there's a pressure at the top of the object. Alright? So the top of the fish, it has a pressure of height of the column above it, density of fluid, and G. But if you go to the bottom of the fish, as we know, pressure will act in any direction. There is also a pressure underneath. But if you go to the bottom, you have that much extra fluid. So if you are at the bottom of the object is deeper than the top of the object, which is true. I mean, a human is about that thick. If you are horizontally in the water, then obviously the difference in density, difference in height between the top and the bottom would not be a very large difference. But there is more fluid acting at the bottom, so there's a greater pressure at the bottom due to that extra change in fluid. That is substantial enough. The pressure difference just between the top of the fish and the bottom due to the difference in height. The only thing that changes from the top of the fish to the bottom is the height of the column of fluid. Density of the fluid is the same, gravitational field strength is the same, so the only thing that creates a change in pressure from top of object to bottom is the change in height. And the change in height from the top to the bottom is just the thickness, if you want, of the object itself. Okay? So it's the height of the fish, essentially. So if you want to determine the difference in pressure between the top and the bottom of the object, greater pressure obviously at the bottom because there's more fluid, you're further down in the fluid, then all you need to do is the change in height between top and bottom, or the height of the object. Let me tell you the expression they say. It says there is an average of 0.75 meters depth between the top and bottom surfaces. Calculate the pressure. It says depth difference. Okay? So the expression depth difference is literally what is the height of the object. What's the difference between the top and the bottom of the object? So depth difference is literally just the height of the object. Alright? So pressure difference will be change in height, top and the bottom of the object, times density of the fluid, times G. Okay? Another definition for upthrust. This is why upthrust occurs, because there's a difference in pressure between the top and the bottom. But what is upthrust? Upthrust is equal to the weight of water displaced. Now in chapter 14 you did a practical to determine the density of an irregular solid. You used a displacement can which you filled to the top. You put the solid in. If it sank to the bottom, it pushed water out through the spout. Okay? If you measured the weight of that water that was pushed out, so using a scale, find the mass times it by 10, the weight of the water that was pushed out will equal the weight of the object. Okay? So upthrust is equal to the weight of water that is displaced, pushed away by the object. That's the definition of upthrust. Okay? Now how do we find that weight? You could use a displacement can, for example. But we're going to use this principle to look at how does the upthrust on objects work for floating objects. Alright? So we have a pressure difference P equals H rho G. This equation is given to you in the exam. You do not have to remember that. You just have to be able to use it and apply it also the principle to this for floating objects. So, if an object floats, then the force that acts down on the object in the water is its weight. So for example, object 1, if you look in the textbook, there's the same example with one more block. You have a floating block here, another floating block, but it's floating lower, and then a block that has sunk to the bottom of this container. Okay? Every single object has an upthrust acting on it. Each one has an upthrust force acting on it. Okay? They're all in the fluid. Object 1 is floating. The weight down must equal the upthrust up. If an object is to float, floating objects, the weight of the object must be equal to the upthrust. Okay? Point number 1. If an object is floating, the upthrust force on the object equals its weight. You cannot hold an object up if you can't balance its weight. For example, if you can't balance the weight, if the upthrust is less than the weight, then the object sinks. Okay? So in order for an object to float, the weight must be equal to the upthrust. Basically what that means is, the water that you're in, the liquid that you're in, so depending on its density, has to provide a support force. So if you ever go and float in a swimming pool, if you ever go and see an object floating in water, you know that the water is being able to provide exactly the weight of the object upwards to help it float in the water. Okay? Now the amount of force up from a liquid, it doesn't have to be the same value. It's not like saying this water in particular can only provide 200 newtons up. So if an object is 200 newtons or less, yes, it will float. But if an object is more than 200, then no, it won't. It's not dependent on the water itself only. Alright? The upthrust provided by a liquid can change depending on the object. Alright? This one is floating, the weight down equals upthrust up, but it's floating higher. This object too is also floating, but it's floating lower. So again, in this case, the weight still equals the upthrust, but what do you know about the upthrust on object 1 compared to the upthrust on object 2? Well, if the upthrust force is equal to the weight of water displaced, and you have a greater weight, you have, in order to have an upthrust that balances your weight, for example, let's say, I'm in water, any one of you are in water, I have a greater weight than all of you, okay? So if we both get in the water and we both float, I have to displace, I have to push out more water than you, okay? So I have to displace more water. In order to displace more water, I have to go lower in the water. It's that simple, okay? But the water will provide an upthrust force for me. Let's say I'm 90 kilograms, my upthrust has to be 900. My weight is 900 newtons. Let's say you weigh 50 kilograms, your weight is 500. You would be box number 1, I'd be box number 2. Weight down for you is 500 newtons. What's the upthrust force? 500 newtons, okay? My weight down is 900 newtons. What's the upthrust force? 900 newtons. So the water is still providing my 900 newtons, but if I'm going to get that 900 newtons, I have to sink lower, because I have to displace more water. My upthrust is greater than your upthrust, because my weight is greater than your weight. But we're still both floating, because both our upthrusts have balanced our weight. The reason I'm floating lower is because if I want to get a greater upthrust from the water, then I have to displace more water. And in order to displace more water, I have to sink lower into it. The more I'm submerged, the more water I push away. Yeah? So it can provide the 900. If the weight goes any greater, for the same object, bear in mind all these objects are the same. They have the same volume, the same surface area at the bottom. So in the context of me and you floating, we assume that the bottom of our surfaces was the same surface area. Okay? Because it changes depending on the shape of the object, more than anything. Alright? Object number 3 is sunk to the bottom. So the weight down of object 3 is not equal to its upthrust. It still has an upthrust on it, but it can only provide a maximum upthrust, which is not enough for this specific object. It's not maximum upthrust for the water is 200 and that's it. But for this object, for the cube, with the surface area of whatever the cube is, then it can provide a maximum, and this weight exceeds that maximum for this shape. So the upthrust force on it is still there, but it's just not big enough to balance the weight, so the weight is greater, so it sinks. Okay? So if weight is not equal to upthrust, there's no amount of water that it can displace, so it's displaced the whole amount of its shape, and still the upthrust wasn't great enough, so it sank. So, if an object floats, weight equals upthrust. If an object weighs more, it requires more upthrust to balance it. If it still floats, it has to float lower to displace more water. Why does going lower create a bigger upthrust? We'll go back. The upthrust on an object is due to the difference in pressure between the top and the bottom. Okay? If I weigh more and I need a greater upthrust force, then I need a greater difference in pressure between the top and the bottom of me. Yeah? How can I get a greater difference in pressure? Go lower. Because again, look, the pressure on an object depends on the height. If I go deeper, I have a higher column of water than you would for box 1. Because I require a greater upthrust force, I require a greater difference in pressure. If I want to get that difference in pressure, then I have to sink lower. Because the lower I go in the fluid, the more fluid I have above me, and therefore the greater the pressure is going to be according to this equation here. Okay? So the pressure difference is difference in height between top and bottom. If you're submerged, it would be between there and there. For the fish, it's between there and there, whatever that height is. Times the density of the fluid. All these upthrust forces are dependent on the density of the fluid, not on the density of the object. Okay? Times the gravitational field strength. Now, how do we calculate the upthrust force? If it's floating, upthrust is weight. It's simple. They say the mass of an object is x, times it by 10 for its weight, and then you know the upthrust is exactly the same as its weight because it's floating. Okay? But what if the object sinks? In this context, the weight down is greater than the upthrust force provided by the water. It cannot keep it up. The water cannot, no matter the difference in pressure between there and there, will not provide an upwards force that balances it. Okay? So how can I find out what is that upthrust force then? I know that it's less than this, but how can I figure it out? If upthrust is due to pressure difference, then the pressure difference on an object is the density of the fluid times by the gravitational field strength G times by the depth difference, which is the difference between the top and the bottom, so the height of the object. Okay? That's the pressure difference. This one is what is the pressure acting down on an object. At the top of an object, what's the pressure due to the column of fluid above it? That's just the height of the column or the depth, the density of the fluid, and G. But what's the pressure difference between the top and the bottom? It's the density of the fluid still, it's times by G, but in this time, it's the difference between the top and the bottom. So it's just the depth difference or the height of the object. Okay? So if I wanted to know here, what is the depth, what is the pressure difference on this object between the top of the block and the bottom of the block? Let's say the block is 1 meter by 1 meter by 1 meter. Okay? The pressure difference is the height of the block, 1 meter, times the density of the fluid. If it's water, then it would be 1,000 kilogram per meter cubed, times G, which is 10. Okay? So 1,000 times by 10, which is gravity, which is 10,000, times by the height difference, which is 1. So the pressure difference between the top and the bottom would be 10,000. Yeah? 10,000 pascals between the top and the bottom. Now, how do I turn that into an upthrust force? Well, going back, I know that the equation pressure equals force over area. So the force up on the object, upthrust force, which I know is due to difference in pressure, and I just found the difference in pressure by density of fluid G and depth difference or height of object. F equals P times A, because pressure equals force over area, force equals pressure times area. But in this case, if I want the upthrust force, F equals P times A, it's not just the pressure at the top, it's the pressure difference. So the upthrust force F equals pressure difference, density of fluid G, height of object, times by area of the bottom of the object. Okay? So upthrust force, pressure times area, which is density, gravity, height of object, area of bottom, which is technically upthrust force equals density times volume of object, because height times area is the volume. Yeah? Area of the bottom of this cube times its height is the volume of the object. So upthrust force equals density of fluid, not the object, density of the fluid it's in, times by the volume of the object, times by the gravity. And that tells you the upthrust force on this. When you work this out, you will find out that it is not as big as its weight, hence the reason it's sinking. Okay? In each of these cases, upthrust is just exactly the same as the weight. Alright? So if you want to calculate upthrust, and it's not floating, so even if you have the weight, if it's not floating, you can't know the upthrust straight away. You have to perform a calculation. The pressure difference between top and bottom, I know upthrust is due to the difference in pressure from top and bottom. So that, I use this equation in the back of the exam. This is not a pressure difference. This is what is the pressure on top of the object. If I want a difference, I just do change in height from top to bottom. So pressure difference on this block, density of fluid, gravitational field strength, and the height or depth difference between top and bottom. Okay? If I want to turn that pressure difference into an upthrust force, then I use F equals P times A, pressure times area, and that is pressure difference, density of fluid, gravitational field strength, times height of object, or depth difference, and then multiply it by the area of the bottom of the object, and And if I put height times area together, that's a volume. So upthrust force on object is density times volume times G. Density of fluid. Okay? And that's it.